There we go. Sorry about that. I had to deal with something. It was cats. It's always cats, right? Welcome back to Chem 121. We're going to keep working on Chapter 6 today. We might even finish it, which would be nice. We still have a little ways to go, so we'll do what we can. Chapter 5's quiz is due tonight, it looks like, according to my notes here. And that should close on Friday, I believe. So make sure that you get that in by the deadline. Yeah, simple as that. All right, we're going to continue where we left off. Didn't we already do this? Yeah, I put my bookmark in the wrong spot. We were actually over... I'm in the wrong window to do that. There we go. We were actually right here, because I showed you this chart. I gotta find my tablet pen here. There we go. Okay. So, I had shown you that we could relate all of the topics that we had talked about together. So over here, we were able to convert grams to moles using the molar mass. And we got the molar mass off the periodic table. And that told us how many grams there were in 1 mole. Up here, to convert particles to moles, so like number of atoms, number of molecules, etc., we use Avogadro's number, and that was just 6.022 times 10 to the 23. And then to go from moles of something to moles of something else, that was if we had like a big formula here. So like something like this. You just take the numbers right out of the formulas to get parts of molecules within the formula. So that was pretty straightforward. We could do that. And we could do all of these 3 parts individually. So what we're going to do now is we're going to put them all together. All right. So let's suppose I give you this problem. This problem is disguised in these other problems as like a more complicated problem, but you actually already know how to do this. And the reason that you know how to do this already is because in this problem, I'm asking you to solve for an aspect of vitamin C. Excuse me. And I am giving you vitamin C. So I am literally just changing this from an element that we were working with before to a molecule. Now, what do A and B mean here on the chart? A equals something. And then importantly, B equals something else. And you might think to yourself, well, duh, otherwise they'd be the same, right? But a lot of students get confused on this part of these problems, where they don't know what to do. Why is my cat... Maya, stop it. She's standing in the hallway yelling at me. A lot of students get confused here, like, how do I use this chart? How do I know when to go from side A to side B? And the answer is, well, are you dealing with a something and something else situation? Here I've got a something. That's vitamin C. And then the question is asking me how many vitamin C molecules are there. These are the same thing, right? So I would only stay on side A. I don't actually invoke something else. Now, if I said I had given you a sample of vitamin C weighing 0.250 grams, how many carbon atoms are there? Carbon is not vitamin C. It's just something else, right? So then we would do this conversion to go from moles of A to moles of B. So hopefully that all rings a bell from yesterday. Or not yesterday, I'm sorry, from Tuesday's lecture. So let's go over here. That's probably good enough. And we're going to solve this problem. I probably should have rebooted my computer again, which is annoying. Let me try something real quick, actually. We'll see if this helps any. All right, so I was given grams of vitamin C to start, and my problem wants me to turn this into molecules of vitamin C. So how do I go about doing this? Well, according to our little chart on the previous slide here, which I'll just expand real quick here, if I have grams of something, I can turn that into moles, which I can then turn into particles. Remember that particles is just our little count of number of atoms, number of molecules, number of formula units, whatever. So we'll do this conversion. So that our units cancel out. Sorry, I'm trying to write slowly so that Photoshop doesn't throw up at me. I need Lentech for this to get the molar mass. Here's the link to Lentech if you don't have it for molar masses, so that's just available again. And then when I type this into Lentech, I guess we'll put this on the screen here, right? When I put this on the screen, there we go. That's probably big enough to see. And I type in C6H8O6, and I hit enter. It gives me a mass that scrolled off of the thing here. 176.12, and that's in grams per mole. So we'll get rid of that, and we'll write that in there. And that number, again, the 176.12, is just simply all the atoms added up on the periodic table, but Lentech calculates it for us. Oh my goodness, I hate when Photoshop is like this. There we go. Finally, our last conversion from moles to molecules. How many molecules are in a mole? Well, it's Avogadro's number, right? There you go. So we'll punch it all in the calculator, and we'll get an answer. 0.250 times 1 times 6.022 was 10 to the 23, divided by 176.12. And we'll make it an exponent, 8.55 times 10 to the 20. All right. Hopefully you are able to do that. All right. Now, if you're using this chart and you just have the chart written out here, what you can do is you can identify a starting place on the chart and a goal on the chart, and then just do your conversions like this. Every time you move to the next box, you're going to write out a conversion. So if I were to go back over here, the steps that we did here, I had my starting value, and then this was conversion 1. And then this was conversion 2. So each of the steps on this chart here is going to be a conversion. So you'll never need to take more than 3 steps, which means you'll never need more than 3 conversions. All right. Let's do a more complicated problem where we actually go across the central part here in the middle. All right. I'm going to give you caffeine because it's early in the morning and nobody has said anything. It's not early in the morning. It's 12:30. But it'll wake us all up. I'm going to give you 0.10 grams of caffeine. That's a lot of caffeine, by the way. How many of the grams of that caffeine sample are nitrogen grams? And we can actually answer this now. So, what are the substances that I'm being given? So I'm being given caffeine grams. So A will be caffeine. But then I'm being asked about grams of nitrogen. Those are different things, so I need to go through this center part, right? And since I'm given a mass to start, I'm going to start here. And I'm going to do something like this, right? How do we know which part of the grams and which part of the particles? It depends on what is given to you. So you know that grams and particles are different things. So one is a mass and the other is something you count. And then you just have to use the appropriate number. Remember that grams to moles is off the periodic table. We can also use Lentech to calculate that for us. Particles to moles is just how many of the thing do you have? And you use Avogadro's number. Because if you have a number of moles, you know how many you have per mole and can do that calculation. So for this calculation here, I know that I have something different for my target than what I've started with. So I'm going to turn whatever I started with, which is caffeine, into moles. And then once oh, hold on. Get down. My cat is trying to knock everything over. Once you have a number of grams, I'm sorry, I'm all miscombobulated because my cat is being really obnoxious. Maya, stop! I'm going to have to lock her out of this room. So we're going to turn grams of caffeine into moles of caffeine. And then once you have done that, you will know how many moles of nitrogen are in that sample because you know how many nitrogens there are per caffeine, right? And then finally, once you get a number of moles of nitrogen, you can get a mass of it. So let's do that over here. So there's our sample. And I'm given a mass of caffeine, so I'm going to turn that into moles of caffeine. Which we then said will turn into moles of nitrogen. And then once I know the moles of something, I can turn that into grams of that something. So there we go. This is our blueprint here. Let's show how we do this. So if I take caffeine, I can do grams of it into moles. How many grams of caffeine are in a mole? Well, if we go over to Lentech, and we type it into our screen here, let's just make this a little bigger. So caffeine is C8H10N4O2. So it says 194.19 grams per mole. So we'll type that in, or write that in our calculation here. And then we'll say moles of caffeine, moles of nitrogen. And then it's this part again. In a mole of the big thing, how many moles of the little thing are there? Well, according to our balanced chemical, not chemical equation, our formula up there, for every 1 caffeine I have 4 nitrogen. And I get that from the formula. There should be a little red arrow next to the 4 on nitrogen. In one of that molecule, there are 4 nitrogens. So in a mole of that molecule, there should be 4 moles of that nitrogen. Okay, great. Finally, we'll turn the moles of nitrogen into a mass of nitrogen. And according to our periodic table, nitrogen weighs 14.007 grams per mole. And so we'll type it all in. 0.1 times 4 times 14.007 divided by 194.19. And scientific notation is annoying. Yeah, that's right. Okay. 0.029. So this step, remember that in 1 caffeine, there are some number of nitrogen. And then all we did was we multiplied both sides by moles. So this number will tell you how many nitrogens are in the big molecule. If I had done instead hydrogen, I would have used this 10. If I'd used oxygen, we'd take this 2, and so on and so forth. The nitrogen, so this is also just Lentech. What does 1 mole of nitrogen weigh? If you go to Lentech and you just type in nitrogen, it'll tell you that. If I can find the button for it, there we go. So if I just go nitrogen, nitrogen weighs 14.01. I know the extra digit because I have a different periodic table I'm using here. But remember that you can also just go to P table here. And then, well, now you can't see it because I got to stretch it out. And if you just click on nitrogen, there it is. Oops, I'm in a different mode because I was playing around with this yesterday. Hold on. There we go. So that's where the 14.007 comes from. 1 mole of nitrogen weighs this much in grams. Remember that the periodic table and Lentech are basically the same thing. They're just tools that are doing the math for you. All right. So now you've seen me do 2 of these. I'm going to give you this one. I have adrenaline, and I'm giving you the same mass, 0.10 grams, which is, again, a lot of adrenaline. I want you to tell me how many atoms of hydrogen are in the sample. So, just like the last problem we did, but instead of doing a mass on the last step, you're going to do a particles instead. So, you're going to invoke Avogadro's number somewhere in there. So, write out your units, write out your path that you're going to convert through. So, what I've been doing in blue here on these sample problems up above my calculation, try and do this sort of thing to guide you. And then calculate the answer. So we'll put this back on the screen here. I'm going to give you about 5 minutes to try it. Then we'll go over the results in just a bit. 1 or 2 more minutes and we'll go over the answers. All right, let's go over the answers. I'm in the wrong screen. Hold on. That's what I want. And then where did my stylus go? There it is. Ah, there's a cat next to me. Sorry. I bonked her with my feet. Let's see. 0.1 grams of adrenaline. I'm just going to write adrenaline as that. And so I have a mass of adrenaline that I'm starting with. And my goal is to get it to atoms of hydrogen. So, when in doubt, convert to moles, right? So if I know moles of adrenaline, I can then find moles of hydrogen using the formula. And if I know how many moles I have, I can turn that into atoms, no problem. So let's do that calculation. So we got 0.1 grams of adrenaline. We'll turn grams of adrenaline into moles of adrenaline. And in 1 mole, there are how many grams? I'm going to just do this on Lentech behind the scenes. If I knew how many, or what the formula was for adrenaline, that would help. C9, H13, NO3. Is that right? C9H13, NO3? Yeah, okay. I got 183.20. Hopefully that's what everybody else got. And so these units will cancel out. And then 1 mole of adrenaline. We can do moles of hydrogen. In 1 mole of adrenaline, how many hydrogens are there? Well, according to the chemical formula, there are 13 hydrogens in 1 molecule of adrenaline. So there must be 13 moles of hydrogen in 1 mole of adrenaline. And then finally, how many atoms are in a mole? Well, we know that in every mole there are Avogadro's number of things, right? Doesn't matter if it's hydrogen, if it's a molecule, if it's a beach ball, if it's a cat. In 1 mole, you have that many things. So let's type that all in the calculator. 0.10 times 13 times Avogadro's number divided by 183.20. And I get a ginormous number. There we go. 4.27. Looks like 4.3. Times 10 to the 21 atoms of hydrogen. Lots and lots and lots of atoms. So whenever you're doing a molecule count, like tell me how many molecules or how many atoms there are, you should be getting a ginormous number because you're going to be multiplying by Avogadro's number at the end. And that makes sense because molecules are extremely tiny, right? So a very small object in a mass that you can see or observe, there should be tons of them in there. Like literal tons. All right. Now these are challenging, so I have tons of them for you to do. So here's table sugar, and I want you to answer all these questions that you can. So whenever we have an atom H or any other element, that means we do. So specifically what you're looking for is you want to be answering this question. How many atoms of this is what's telling you that, oh, okay, my answer should be here. And to do the last step, you got to go from moles to particles. And you know how many particles are in a mole, right? Remember that the word particles is just a catch-all. It could be atoms, it could be ions, it could be molecules, it could be whatever. What is the intent is count the number of things using Avogadro's number. So whenever you see this step, it's not linked to an element, it's linked to what unit you want. All right. So go ahead and do that over here. So I'm going to give you 0.522 grams of table sugar. Here's the formula for table sugar, or sucrose. I want you to tell me how many particles of table sugar there are. In other words, how many molecules. How many moles of O, how many grams of C, and how many particles of hydrogen. In other words, how many atoms. All right, there's my 4 questions. I'm going to give you a little bit to work on this, and I'll be happy to answer questions in the chat, of course. We'll check back in with you in just a little bit. So see you soon. 1 or 2 more minutes, we'll go over the answers. All right, let's go over the answers here. We'll go to this screen. All right, what do we got? So I have, for all these problems, I have 0.522 grams of sugar. All right, so what I need to do is figure out how many particles of table sugar there are. So I have a mass of sugar. First, I want to turn that into moles of sugar. And then I want to turn that into molecules of sugar. And that will tell me how many molecules of sugar I have, or particles. I'm just going to write sugar because writing out the whole formula is kind of silly. All right, how many grams are in a mole of sugar? Well, according to Lentech, the molar mass of this is C12H22O11, 342.30. And then from there, we go from moles to molecules. And in a mole of anything, we'll cancel these out, there are Avogadro's number of molecules. So we should get 0.522 times, oh my goodness, scientific notation, why? 6.022 times 10 to the 23 divided by 342.30. And now I need scientific notation. 9.18 times 10 to the 20, molecules of sugar. So that's the first problem. All right, let's do the second one now. How many moles of oxygen are present? So we'll start at the same spot. We're going to be starting with this over and over here. And this time we want to go mass of sugar to moles of sugar. And if I know how many moles of sugar I have, I know how many moles of oxygen are in it because I know the formula. It's right there at the top, yeah? And so these units cancel out, and I know that in 1 mole there are 342.30 grams of sugar because it's still the same molecule off the periodic table. And then I know that in a mole of sugar, cancel those out. How many moles of oxygen are there? Well, according to the formula, there are 11 oxygens per sugar. So this should give me my number of moles of oxygen, because that's the unit that's left over. So 0.522, 11, 342 point, oops, hold on, 2.30. 0.0167 moles. All right, that's the second one. Let's do the third one here. How many grams of carbon are present? So again, start with the same sample here. So is 0.017 okay? You need to have 3 sig figs because your answer up here has 3 sig figs. Or the number you started with has 3 sig figs. And this one had 4, or 5 actually. These are counted, so they're exact. Why didn't we use Avogadro's number? Because I didn't ask you for a number of particles of something. I asked you for a number of moles. So we use Avogadro's number for the first one because I want to know the number of particles of sugar. But in the second question, I want to know the number of moles. They're different units. Remember, your units are going to dictate what you do to the problem to solve it. Can't just throw units around randomly. If I want grams, you use the periodic table. If I want moles, you use the formula. If I want particles, then you use Avogadro. Yeah, if you do moles A to moles B, it stays moles because what are we writing down? We're writing it in moles, yeah? I wrote moles of something and moles of something else, so no Avogadro in there because I did not use particles. So if you aren't writing out your units every time, you're going to get stuck. So make sure that you are writing out your units like I am. I don't write out these units just because I'm the instructor and I have to. I write it out because it's how you solve the problem. I am literally showing you the easiest way to solve the problem, and if you take any shortcut, it is at your own peril. So be real careful. Write out all the units every single time. I cannot stress that enough. Because the second you stop writing down units is the second you're like, oh shit, what does this mean? And then you go back and look at it the next day and you're like, I don't know what this was. It's just a bunch of numbers, right? And we don't want that. All right, so to go from grams of sugar to moles of sugar, we've done this 30 times today already, so that's how much the mass of 1 mole of sugar is, according to Lentech. And I didn't write down what we were solving for on this problem, so we've got grams of sugar. Gives us moles of sugar. So the units of problem 2 are moles of oxygen. So we go grams of sugar, moles of sugar. This problem wants us to do grams of carbon, so we need to first do moles of carbon to get to grams of carbon. So we'll do mole sugar, moles of carbon. And in 1 mole of the molecule, C12H22O11, how many moles of carbon are there? Well, according to the formula, there are 12, right? Because it's C12H22O11. And then we can do moles of carbon, turn that into grams of carbon. And according to the periodic table, there are 12.011 grams of carbon per mole of carbon. And so we get for that problem 0.522 times 12 times 12.001 divided by 34230. 0.220 grams of carbon. And we get that number because of sig figs. All right, last problem. How many particles of hydrogen are present? In other words, how many atoms are present? This first part's been the same for all these problems, which is where I'm just immediately writing it down. So let's plan out our units. We got grams of sugar, which will turn into moles of sugar. From there, I can do moles of whatever I want to. This problem wants to talk about hydrogen, so we'll do moles of hydrogen. And then we can do atoms of hydrogen. So we'll do moles of sugar, moles of hydrogen, and in 1 mole of sugar, how many hydrogen moles are there? According to the formula, 22. And then finally, in a mole of anything, how many atoms are there? Well, in 1 mole of atoms, there are Avogadro's number of those atoms. And so that would be 0.522 times 22 times Avogadro's number divided by 342.30. And that's way too big, so let's do this. 2.02 times 10 to the 22. Is what I got for that. All right. We went way past our break, so we'll have to take our break now. Let me get the homework practice on the screen real quick, though, before we do that. So there's the homework practice on your screen now. Lots of problems to choose from for these. Make sure you do a lot of these practice problems, because it's very difficult to do these just after doing 1 or 2 of them. Practice makes perfect, right? So do as many of these problems as you can, and then go to the worksheets and try those there too. All right, we're going to take a break. Let's put this up on the screen. I don't have my timer. Let me get that real quick. No, I don't want to update it. No, never update anything. All right, let's start this, and I will see you in about 10 minutes. Hi everybody, we're back. I'm gonna move the mic a little bit. There we go. Alright, the next section, what we're going to do is we are going to bounce chemical equations so that we can use them in sort of the same manner that we just used them for doing calculations in the previous exercises. So, let's go ahead and get started with that. Hey, we're going to do actual chemistry. So this is how chemistry is represented in the context of a laboratory experiment that you could do, for example. So I might give you something like, say, I react hydrogen and oxygen together, and the product that is formed is water. So what I would do is I would do something like this. I react hydrogen with oxygen, and water is formed. And it looks something like that. Now, as we're going to find out, we're going to need to do some stuff to this. For example, this is a better version of the equation. And then this is even more informative, too. Oops, sorry, that should be a G. That's also a G. So why am I adding all this extra information? Let's talk about what all of this information means. I can't find my erase button. There it is. Oops, that's not right. All right. So by writing out a reaction in this way, we can use it to do different calculations that we're going to encounter, but also to conceptualize, okay, this is what I'm making from these things. So we're going to use this statement as our sample experiment because there's a lot that I can use this for. All right. So sodium and water react vigorously to form sodium hydroxide and hydrogen gas. I'm going to transform that into a chemical equation for you that looks like this. And then we're going to talk about all the parts of it. All right, so let's first talk about this arrow in the middle and what it means to be on the left side versus the right side. In a chemical reaction, the left side is going to be what things you are going to do for your reaction. In other words, they are the reactants that react with themselves. I will put the reactants in the container, and then I shake it, or whatever. If the reactants are what react, then what must be the result that goes on the right? Well, those are what you produce, or the products. It's not advancing. There we go. So reactants on the left, products on the right. The arrow in the middle always points from reactants to products. Now you might think, well, okay, duh, because we just said that. The reactants are on the left, the products are on the right. Well, it turns out that you can reverse the direction of the arrow, and there are reasons that we would want to do that. We're going to talk about that in Chapter 8 and 9. Generally speaking, though, if I have a backwards arrow, it is accompanied by a forwards arrow, and it would look something like this, where I have a reaction that goes in both directions. And so we'll see that in Chapter 8 and 9. All right. After each component in my chemical equation, I have a set of parentheses and then a character. These letters represent the phases that we would encounter that substance in. Now, you probably recognize what S, L, and G are. Those are just solid, liquid, gas. But AQ is actually a little bit special. AQ means that it's dissolved in the water. And if it's ionic, it dissociates into specific ions. So what NaOH AQ means is that... Wrong end of the pen again there, sorry. I actually have these two things separately floating around. So if it is an ionic compound, it will split into ions. If it's a molecular compound, like, say, CO2, it does not split into ions. It just is dissolved in the water. Much like in your carbonated beverage, you would have CO2 AQ. Speaking of carbonated beverage, I had to take a swig of my polar seltzer here. All right, the last thing that we're going to care about are these numbers in the front here. You'll notice that the arrow over here on the right is pointing at a blank. And a blank represents a 1. These numbers are written here so that we can do something specific. It's called balancing an equation. And that's going to be the focus of this section, is we're going to balance some chemical equations. Now, why do we need to balance an equation? Well, it turns out that the equation that is going on would obey all the physical laws that we observe. So one of those is the conservation of mass. I cannot create elements out of nowhere, nor can I destroy them. I have to have the same amount on both sides of the equation. What that means is that I have to take inventory and count the number of sodium on the left and the sodium on the right to make sure that they're equal. If I start with 1 sodium but I ended up with 2, that would imply that I've created sodium. That if I run the reaction as written, I would just generate sodium endlessly. Now, you can't do that. Obviously, I can't just create elements out of the ether. That would not be possible. So we have to write a reaction that actually represents what's going on. So that's where the conservation of mass requires us to balance the equation. All right. So this is just about the conservation of mass. Hey, you can't create or destroy matter. You have to use all of the stuff. Therefore, your reaction must be balanced. Always, always, always check to make sure it is. Now, on any exam or test that I will give you on Canvas, I will either tell you, here is a balanced equation, and then I will balance it for you, or I will say, here is an unbalanced equation, and then I will put blanks in which you will have to fill in the numbers yourself. For an unbalanced equation, obviously you have to do the balancing, so you'll have to do some work. For a balanced equation that I give you, double check to make sure that it's balanced real quick. Just in case I have made a typo or something like that. It is generally a safe assumption to say, oh, the equation's been balanced, so it's probably all right. But very rarely that does happen, that somebody makes a mistake. Whether it's me or somebody else, it happens. All right. The next thing we're going to do is we're going to actually balance an equation. So I'm going to just skip over this text telling you how to do it, and I will go straight to the example here. So I'm just setting up my PowerPoint, but Photoshop here. There we go. That's what I want. All right, so this is the equation that we're going to be using here. And so what I'm going to do is I'm going to draw a line right down the middle here to sort of bisect the equation into 2 halves, the reactants half and the products half. And then what I'm going to do is I'm going to go like this. I'm going to write out each of the elements that are present in my equation. So I have a carbon, I have a hydrogen, I have an oxygen, on each side. So what will I do now? Well, if I'm balancing the equation, let's see where we're starting, right? How many carbon do I have on the left? Well, there's only the C and CH4, so I'll just write that, 1. How many hydrogen are there? Well, it's a CH4, so we'll write that. We got O2, so there's 2 oxygen there. Now we'll go to the right side. I have 1 carbon in CO2. I have 2 hydrogen in H2O. How many oxygen do I have? Well, I have 2 from CO2, and I have 1 from water, so that means I have 3. All right, is our equation balanced? No, I have destroyed hydrogen and created oxygen. Can't do that, so now we need to balance the equation. So what do I do to fix that? How do I balance the equation? So what I'm going to do is I'm going to put a little line in front of each of these to give us some space to work. Now, if I'm going to balance the equation, I can really only put in whole numbers, so that means that I'm going to be putting more matter on a given side. That means that all the numbers will only go up. Numbers can't go down because I'd have to cut things in half, and you can't have fractional molecules. So with that in mind, where should I put a number on one of those red dashes? So like if I put a 2 here, then what would happen to my equation down below? Or not equation, I'm sorry, my inventory down below. Well, I would gain a carbon, and I'd gain 4 hydrogen. Would I be balanced? No, I'd actually be further away. So putting that number there doesn't really make much sense. So we'll just undo. And we'll undo, well, if I can click on it, we'll undo this one. So what's the most logical place to put a number? Why didn't it? Oh, it is right there. Okay, never mind. Sorry, I was looking at the wrong thing. I want you to tell me where I should put the first number, and then I will do that, and we'll see what happens. So H is a good spot. I don't have H in my equation, though. I have H2O. So in front of the H. So you want to work here. What number should I put in this spot? O is also unbalanced, but I heard H first, so let's start with that. Really, there's no wrong place to start. Well, I guess there are wrong places to start, but I just realized you can't see my arrow because it's not in what I've caught here. There we go. So we're going to start here. Let's put a 2 here like somebody suggested. And let's see what that does for our equation. Or our balance down here. So I have CO2. It says CO2. So that didn't change my carbon. H doubled because I have twice as many water. And then for my oxygen, I still have 2 from before, but now this has become 2 from the water because I doubled it. So now I have 4 total. So this is good because I balanced out my H's, but my O's are still not done. So now I need to do something. And Lynn has the right idea there. So now we can do 2O2. So if I put this 2 here, then doubling my oxygen gives me that, and now everything's balanced. So all my carbons are matching, my hydrogens match, and my oxygens match. So everything is balanced, and the reaction is done. So as written, if I react 1 CH4 with 2 O2 molecules, I will produce a CO2 and 2 water molecules. I won't be creating any atoms out of nowhere. Everything is balanced, so this must be what the reaction does when we encounter it. All right, very good. So that's the gist of figuring out how to balance an equation, is playing with your inventory and then just tinkering numbers left and right and seeing what happens. Now, let's look at a strategy that's going to help us determine the answer a little bit more effectively. Here's my carbon on the left, and here's my carbon on the right. And what that tells us is that this number right here that I've highlighted and this number are related. In other words, whatever number I put in front of CH4 has to be the same number I put in front of CO2. Otherwise, I would never have the correct number of carbon, right? So if I put a 5 in front of the left one and a 3 on the right one, I would not have the same number of carbon, and I'd have to go back and balance it later. The same thing is true about hydrogen for right here. So here's my hydrogen and how it links up with this guy. The number that's highlighted, green for CH4, has to be half as much as the coefficient for H2O, right? Because there are half as many hydrogens in H2O as there are in CH4. In other words, if I can get my pen with the right color here, this number times this number needs to be equal to this number times this number. I just realized I'm writing product when we're talking about reactants and products. I want the product as in multiplication. So that can help you solve for these numbers more effectively by realizing where do these atoms end up. And if you can see a pattern like that, you can then quickly go and fill in all the numbers. All right, so my slides are just going to walk through the first one of these like that. I'm just going to give you this next one. I want you to balance this equation. So I'm going to put some blanks down. And we'll go over the answer in just a second, but I want you to try and balance it on your own. So go ahead and try it. All right, one more minute. We'll go over the answer. All right, so we're going to do that right on the screen this time, I think. So I only have 2 elements this time. I've got nitrogen and oxygen. So I got 1 nitrogen and 3 oxygen over here because I've got 1 plus 2. And then on the right side of the equation, I have 1 and 2. How do I balance the equation? Well, unfortunately, the only place I can really start is on the right here. So I had to do something like this, which makes this wrong. But it does mean that I only need 1 of each now. So if I do this, I get a balanced equation. So the balanced equation here is 2NO plus O2 makes 2NO2. Ooh, excuse me, sorry. All right. Now, in the middle number, we don't actually have a 0. Remember, the blanks are 1, even if the 1 is not shown. If it was a 0, we wouldn't write it at all, right? 002 would not show up in the equation. All right. Now, there are some little tricks that you can use that can help you out here. If you see common polyatomic ions like phosphate right here, just writing out phosphate instead of P's and O's can help you. It saves you a little bit of time, and then you're just counting phosphates. This is particularly important if you have other sources of phosphorus and oxygen. This will save you a lot of trouble. If you have the option of where to start with the most complicated molecules you can. Doing the simplest molecules last means that if you're only affecting one element, you can get to an ending state. As opposed to, oh, I need to change carbon, but the only thing that I can change carbon in is attached to 4 other elements, and then you adjust your carbon, and then everything else falls apart. You have to do more work. That's no good. Hydrogen and oxygen are typically by themselves. Those are the ones you want to do last. And then my last bit of advice is if you end up with gigantic numbers, erase everything and start over. The reason that you may end up with gigantic numbers is because of a math error. If you make a math error and that keeps propagating through your calculations, i.e., you have oxygen in 2 places, but you just keep missing one and you don't remember to add it in there, then you will never ever get a balanced equation. You will end up with like an arms race where the left gets bigger and the right gets bigger and the left gets bigger and the right gets bigger. And it goes forever and ever and ever. So if that happens to you, just start the calculation again and balance the equation from scratch to see if that maybe you made an accounting mistake. I'm going to give you a bunch of these. I don't know why the first 3 appear on their own, but there you go. So I want you to balance these 5 equations. I'll give you like 5 or 6 minutes to do that, and then we'll go over the answers together in just a little bit. I just got a message that my connection screwed up, but it looks like it's still okay. So we'll do 2 or 3 more minutes, and then we'll go over the answers to all of these. All right, let's go over the rest of these because we only have 5 more minutes left. We'll go up here. Yeah, oh, that's the wrong way. Let's do these first 2 here. So we got, I'm going to write the problems in my box here. So we got Fe plus O2 makes Fe2O3. All right, so I got Fe, and I got O, Fe, and O. So I'm going to count these. So I got 1 iron on the left, and I got 2 oxygen on the right. 2 iron on the left, and 3 oxygen on the right. And so now I need to figure out where to start. So I should either start here with iron or oxygen. But no matter what I do to this, so if I put this 2 here, I'm never going to get 3, right? So that's not going to help me terribly much. So what I need to do is, if I do this, I will get an even number, because 2 times 2 is 4, and then 2 times 3 is 6. And now I can put a number here that will give me the correct number, right? So 3 times 2 is 6, so I have 6 oxygen on both sides. And then I just have to put the right number here so that I have the correct number of iron on both sides too. So for the first equation, you should have 4, 3, and 2. And then for the next one, we have that. So I got one of each, because it's what my formula says. And I got one and then two. All right. Obviously, I need to do something over here, because I have more oxygen on the right, so I got to balance that out. So if I put a 2 here, I now have 2 of each, because 2 times 1 and then 2 times 1. And then I'll just do this, and it's done, right? All right. Those are pretty straightforward. Let's do these more complex ones. Remember, if you need to, you can pause the video. There we go. We'll do the same thing we did. We got carbon, we got iron, we got oxygen. Carbon, iron, oxygen. I got 1 carbon by itself over here. I got 2 iron and 3 oxygen. I got 1 iron, 1 carbon, 2 oxygen. All right, so what do I do? Well, I have this issue with oxygen here. No number that I enter here is going to give me 3, right? I'm going to get an odd number. So let's do something like this to get this off of an odd number and onto an even number. So 2 times 2 for iron is 4. 2 times 3 for oxygen is 6. That means that I can do this now, because 3 times 2 would be 6, but it also changes my carbon. And now it's easy to fix. So this becomes 4, and this becomes 3. So you can see the gist of what I'm trying to do here is I'm trying to make it so that I can change other elements to match my numbers. So here I could never get 2 to match 3, but I could get 2 to match an even number. So if I can multiply this to get it to be even, I could work with that. All right, so the next one, we got sodium phosphate plus magnesium chloride. Use magnesium phosphate plus sodium chloride. Now remember, I'm just going to keep my phosphate together, because that makes it a little simpler. And then when I go count these, let's see here. So I got 3 sodium of phosphate, magnesium, and then 2 chlorides. Over here, I only have 1 sodium, 2 phosphates, 3 magnesium, and 1 chloride. So we have some work to do. Now, I want to start with the most complicated things first. So I'm going to try and balance phosphate. It's the most complicated molecule, right? So if I want a second one of these, I can put a 2 here. That gives me 2 phosphate and 6 sodium. And then looking at where my phosphate is, it's in this magnesium thing. So let's try and balance magnesium next, because that'll make sure that this molecule is balanced, and I won't ever have to touch it. So I need 3 here, don't I? So the only way I can do that is to do this, which makes my chlorine 6. And then all that's left is just to balance sodium and chlorine, which I do that over here. You're going to find that with a lot of these equations, when you balance them, it starts off pretty awful looking, but then it quickly refines to there's only one molecule that you want to change, and it will solve the problem. You might have to go in a few circles a few times as you do this, but you'll eventually get there to the point where it's like, oh, I'll change this one, and oh, it's done, and it's a nice surprise. I've gone over time, but that's okay. We could do the last one here. I think I might be out of... Yeah, so I gotta hit delete here. Ooh, that's not what I want. Sorry, I was on the wrong screen when I hit delete. So this goes away. OBS is like, are you sure you want to delete your scene? And then suddenly everything just turns off. It's like, oh, goodbye. No more screen. Don't want that. There we go. So we got this. We'll split this down the middle here. We got copper, chlorine, aluminum. There you go. All right, so what do we do here? Well, I got the same situation, right? So there's no number I can enter for my chlorine that will make these work. Well, if chlorine over here comes in 2s, and over here it comes in 3s, what product should I shoot for a total chlorine? Well, if I just swap their numbers, that will give me 6, right? So we know that works. Now I just have to balance out the rest of the things. So I have 3 copper and 2 aluminum. And then balancing the equation from there is just trivial. There you go, it's done. So hopefully that gave you some like sneaky tricks that you can use to do this. But really the trick that it's going to come down to when you're balancing these equations is write everything out and do the math. Like actually count stuff. I think that the issue you might have had earlier was when you have something like, say, like whatever this is, and if I was doing something like this, it's like, okay, well I have 1A and 2B. Well, if I put this number here, you aren't going to say, oh, that there's 4B, because you got to count this one too, right? So there's actually 5. So when you have multiple sources of different elements, make sure that you are adding all of those elements together. So that could be the issue of what's happening, is if you get stuck, you're like, well, how did I get this number? It's probably because there's a second source of it on that side. And so just be mindful of that, because when you are taking your inventory is everything at the bottom. So everything on the reactant side. And everything on the product side would be on the other side of the line, and so on. All right, so there's the homework practice for that, and we are out of time, so I'm going to call it a lecture there. I do want to thank everybody for coming out to the lecture. If you have any questions, please let me know. Quiz number 5 is due tonight. We're probably going to finish Chapter 6 on... What day would it be? Tuesday? So I'll post the quiz for Chapter 6 next week. And then we'll hop into Chapter 7, and then we're kind of on the home stretch from there, so... Alright. Is there anything else that I want to say? No, I don't really think there is, so I'll just hit this button here. Play this music. That means we're almost done. Have a wonderful weekend. Oh, wait, hold on. Let me pause the music here. We didn't really talk about lab number 3. But lab number 3 is just, I believe it is, I want to say it has to do with Chapter 5 stuff. So... ask me any questions that you might have about that on Discord or over email. I don't think it's that complicated, but I will open that up so that you can work on it over the weekend. It'll be due next week. Yeah, that's really all I have to talk about that, so we'll just start this music again. There we go. Yeah, let me know about any lab questions, and we'll finish chapter 6 next week. So have a wonderful weekend. Take care.